So in the last class, we discussed about the fabrication of MOS transistor, because this is important to know how the MOS transistor fabricated in the device class also, right? Okay, so yesterday we discussed about the front end of line processes. That means the wafer start to the silicide formation. So once you have, so actually you are here. So here you could see that after you have your sourced and implantation, right? So then you deposit cobalt and anneal it. So the cobalt will react with silicon and form cobalt silicide, right? So this cobalt silicide is a highly conducting material. So this is done just to decrease the resistance of source and drain, right? So once you have this cobalt silicide, right? So cobalt silicide is used in 130 nanometer process. So if you go to means 90 nanometer or 65 nanometer process, the industry has moved from cobalt silicide to nickel silicide, and they are now talking about nickel platinum silicide, because as you move from one technology to other technology, so your dimensions also decrease. That means when you're talking about contacts, contact resistance also increases, right? So with the increase in contact resistance, so we want to means basically we don't want increase in contact resistance. That's the reason industry moves to different materials with time, right? So cobalt silicide is used for 130 nanometer CMOS technology. So when you move, means in advanced CMOS technologies, people more use nickel platinum silicide. All right. So once you have the contact, so next step is the formation. Once you have the silicide, the next step is the formation of contact. Right. The contact will connect the front end your device front end to device back end. Right. So basically, how it is done. So once you have your silicide, then you deposit a oxide layer. So this is called means interlayer oxide or interlayer dielectric, um, right? So this is called interlayer dielectric. So you deposit interlayer dielectric, and in this case this is silicon dioxide, right? And so you deposit a interlayer dielectric, then polish it, right? The polish means you have to make the surface of the flat, right? Let's say you have your transistor, right? So you have your transistor, so everything is done. So you have silicide also here, right? Then you deposit oxide and make then planarize the surface, so that you have a plane surface, right? And this part is oxide, right? So right, then the contacts, right? Then you etch holes, right? The hole, the contact is nothing but you just etch holes and fill this hole with tungsten, right? So so basically here you see, means when you draw a transistor layout, right? So you have your active region, and this is your gate, right? Then you have to contact your source drain and gate. So basically you have a contact when you draw it, right? So you draw contacts, like the contacts are drawn as squares, right? And your gate contact here also, right? So so these contacts, basically what is done is just you deposit interlayer dielectric, planarize the surface, then you etch holes, right? So then you etch holes. These are the holes that you have etched, right? And then fill these holes with tungsten, right? So basically this hole is filled with tungsten. That is again a deposition process. Tungsten is this is done by chemical vapor deposition, right? You fill holes, right? Then you planarize again, right? So planarize means polishing, right? So you are taking the wafer and polishing it, so to planarize the surface, right? So so this is what you will have now, right? So you have silicide here, right? Source and drain silicide, and this is the contact, right? So once we have formed the contact, the next step is the metal one, right? So you have to go to different metal levels, right? So for the metal, so this is the some TM picture of some contacts. You could see this is the contact on source or drain. This is the contact on gate. because gate is at a height, right? And that's why the contact is, I mean, so you see that this contact is on gate, right? And this contact is on the source and terminal. Okay, so then we have to have metal one, right? So the first metal level, right? So means in a typical IC, depending on the technology, we have multi-layer metals, right? In 180 nanometer CMOS technology, we have almost we have 4 to 5 layers of metal, right? But in 130 nanometer, we have more layers of metal. In advanced technology nodes, like when we're talking about 28 nanometer, 22 nanometer, or 14 nanometer CMOS technologies, so there the number of metal layers is almost 10 to 11, right? Okay, so we are talking about the first metal layers. So, so basically, how is it done? So again, you have to deposit a intermetal dielectric. So this is called intermetal dielectric because these dielectrics will come between different metals, right? So this is the intermetal dielectric, and this is a low K dielectric because capacitances are is a main issue nowadays between different metal levels. So, we use mostly the low K dielectric, dielectric with a lower dielectric constant than silicon dioxide, right? So you deposit, right, again by CVD, or this is mostly done by the plasma enhanced CVD process, right? I told you in the last class. So now, then you photolithography, right? So you do photolithography. That means you mask some regions, and right, and then you do the etching, right? So you etch it, right? So here you see, means you have removed some portion of the dielectric. Then that portion you fill it with metal, right? So you fill it with metal, and in 130 nanometer CMOS technology, the copper is used for the first time. So before 130 nanometer CMOS technology, right? So when we're talking about 180 nanometer CMOS technology, so people are using aluminum. So now in 130 they moved from aluminum to copper, and so aluminum is mostly deposited by sputtering process, right? But when we're talking about copper, so copper is deposited by electroplating, right? So basically this process is electroplating. So by electroplating you deposit copper, right? So you deposit copper, then you polish it, right? When you polish it, then you have your metal, right? So this is, so see, this is again a typical, if you look at, so this is my NMOS transistor, and this is my PMOS transistor, right? So this is nothing but an inverter, right? So inverter in the sense, if you know inverter circuit, right? CMOS inverter. So I have my PMOS and NMOS, right? Right. So for the PMOS, for the NMOS, this is your drain and source. For the PMOS, this is your source and drain. So you see here in this case here, right? So this is the source of your NMOS transistor. This is the drain of your NMOS transistor. This is drain again of the PMOS transistor. This is source, right? So this is how it is connected, right? In the integrated circuits, this is just a very simple circuit, right? But when you're talking about ICs are more complex circuits, right? So this is how you connect, right? So you have contact. So you have contact for every terminal of a transistor, right? Then this here the drain of both PMOS and NMOS are connected at metal one, right? So it means for an inverter, you may not need more layers of metal. You could deal with this, right? If you are only fabricating a simple inverter, right? So inverter will work, right? So you have to take this metal, put it to ground, right? This to VDD, and this your output, right? And your gate metal is not shown, right? So you could also have your gate metal where you could give the input, right? Okay. So so this is metal one, but for this simple inverter circuit, yeah, you can do with only metal one. But when you are multiple transistor, millions of transistor in a typical ICs, you have thousands or millions of transistor. When you're talking about a microprocessor IC, we have billions of transistor, right? In a typical, so when you're talking about Ryzen processor, right? Many of you are using Ryzen processor, right? In the Ryzen processor itself, we have around 8 to 9 billion transistors, right? I'm talking 8 to 9 billion, right? Billion transistors, right? And these transistors will be connected, right? So they cannot be connected by a single metal layer. That's the reason we have different layers of metal, and transistors are connected at different levels, right? Okay, so this is metal one. So when I'm talking about metal one, right? So as I told you, we have different levels of metal, layers of metal. So let's say this is metal one. I might have metal two, so metal three, and so depending on the number of metals, this is, let's say, metal 10, right? In advanced processes, right? So metal 1 and metal 2, so they are mostly connected by something called, we call it via, right? So different metals are connected by vias, right? So this is called via 1. So via 1 connects metal 1 and metal 2. Via 2 connects metal 2 and metal 3. And similarly, via 9, right? Via 9 will connect, via 9 will connect metal 9 and metal 10, right? Right. So when you're doing the back end, right? So when you're doing the back end, so basically we have to have metal, then via, then metal, then via. This is how we'll fabricate, right? Okay. So this is a cross section of a typical metal one, right? So when you take the cross section in TM microscope, this is how it will look like. Okay, so now you have to do via one, right? So via one, if you go to next metal level, metal two, metal one, metal two, there will be via one in between, which will connect metal one to metal two, right? So again, for the via one, we'll do the same thing. So we'll deposit dielectric. So this is again interlayer dielectric or intermetal dielectric in this case. I mean intermetal dielectric. So you deposit dielectric, then you do the then you put your via mask, right? So do the photolithography, right? Then you etch holes in the dielectric, right? And this is done by photolithography. Then you deposit your via metal, and in this case also this is so when I talk about metal, right? So this metal here is copper, right? So right, this is copper. So your via is also made of copper, right? So copper is mostly deposited by electroplating, not mostly, only deposited by electroplating, right? Then you polish it, right? This is how you polish it. Then you have metal one, and on top of that via one, right? So once you have metal one via one, then you have to do metal two, right? So metal two will follow the same process. You deposit dielectric, mask it, etch it, then you again deposit, right? This is how it will go to metal two, right? So you see, this is your again intermetal dielectric. Then you mask, etch, then you fill. I mean, it's basically you deposit metal and polish it, right? And if you polish it, then this will be metal two, right? So this is the first level of metal here, right? And this is the second level of metal, and this is your via one, right? So this is how you will go, right, to different layers of metal, right? And if you see a cross section here, so this is your metal one in this case, right? You have metal one. So this is your via one, right? Via one, and you will go to metal two, right? Metal one, via one, and you will go to metal two. In this picture also, this is metal one, this is via one, and this is metal two, right? So this is how you go from one metal to different metal in the circuits also, right? Uh, right. Um, Okay, so this is about metal two, but another thing which is typically done. So let's say when you draw, right, when you're doing the layout, right. I should not spend more time on the layout in this course, but let me tell you one thing. So let's say this is your metal one that you have drawn, right, and you'll then you'll have via one. So metal two and metal one, right. So metal one, metal two, both are orthogonal to each other, right, right, because you don't want your metal 2 running parallel to metal 1, because if it runs parallel to metal 1, then there will be capacitance, right? I don't want much overlap between two consecutive metal layers, right? That's the reason if the metal 1 is drawn in one direction, metal 2 will be drawn in the other direction, right? And the metal 1, metal 2, they are connected by the via, right? So your signal can go from metal 1 to metal 2 via via, right? So this is via 1, right? But keep in mind, metal 1, metal 2 are drawn orthogonal to each other. So this is a typical cross section. So you could see your transistor is here anyway, right? And you see this is so this is one layer of metal, right? So this is one layer of metal. So this is metal 2, and this layer, the below layer, is metal 1, right? So you see metal 1 and metal 2, so they are running orthogonal to each other, and metal 1 and metal 2 are connected by via, right? Right, so so you could see from here, right? So this is a packaged IC which is unpacked, and this is something called reverse engineering, right? Many times companies do reverse engineering. So if you could buy a IC and remove the packaging, everything, and you could see how this IC was fabricated. So basically, means you could see also different layers of metal. So here you see, you could clearly see that one layer and other layer, the next layer, they are mostly orthogonal to each other, right? So this is a typical, this is no rocket science, because when we're designing, when we're doing device design or doing the device layout, so we have to make sure that the parasitic resistances and capacitances are less. And the only way to reduce parasitic capacitances is to run lines perpendicular to each other, right? Orthogonal to each other. Okay, so okay, so this is the X section, but I have metal 1, via 1, metal 2, then via 2, metal 3. But at the end, right? So this is at the end, right? So this is called terminal metal, right? Last metal, right? And the last metal is always exposed to the environment, right? So basically, when you look at packaged IC, so your last metal is always exposed to the environment, right? And this is the reason you your last metal cannot be copper, right? So copper, if you leave it in room temperature for some time, copper oxidizes, right? So that's the reason your last metal in most of the ICs is made of aluminum, right? So your last metal, because that will be exposed to the environment. So aluminum is a stable material than copper. So so you last metal is you do aluminum. So last metal, basically, let's say your last metal level is ninth metal, right? And after that, you have to deposit. I have to do terminal, means last terminal metal. So then basically you do the same thing, like basically you deposit a intermetal dielectric, then you do the lithography. Lithography, you remove some portion of dielectric and fill it with the next metal, right? So so here I have done the lithography, removed your intermetal dielectric. Then you deposit in case of aluminum, right? And here it is used aluminum copper. Because aluminum copper here it is used because aluminum has higher resistivity. That's the reason industry moved from aluminum to copper, right? Aluminum has higher resistivity. I don't want high resistivity lines. So but here they have used aluminum copper. This is a refractory material. That means it's a combination of two metals, right? And this is means this is better, right? So in resistivity wise, it is better than aluminum, and it will not also oxidize, right? So once you have the terminal metal, then I could pattern the terminal metal. So this is what you see, right? So basically, this is where you do the measurement. This is your terminal metal, and you could connect, you could give voltages and currents to this terminal metal, right? That's what you see in the outside, right? Um, so, so this is the whole structure that we have seen. We have seen how to fabricate this structure. So, the down the means down we have your MOS transistor is so if you look at this is a stack, right? So you could look at this as a multi-story building, right? The multi-story building, your ground floor is your transistor, right? So your transistor, your active devices, whatever you fabricate, let's say in your circuit you have transistors and capacitors or resistors, so all of those are in the ground floor, right? And your first floor, second floor, third floor, all the floors are metal lines, right? So basically you could see here, right? So this is your MOS transistor, right? And this is the front end of line, right? So this is the front end of line part. So all this front end of line processing, and then other one is the back end line. So these are the metal stacks, right? Uh, so here you could see if this is metal 1 and this is metal 2 and you have here 1. Similarly, metal 3 and you have here 2. Metal 4 you have here 4. Metal 5 then you have here 5. Metal 6 here 6. Right? Oh, I did some mistake. 4, 5. Then metal 7 you have via 6, then metal 8 you have via 7, this is metal 9 you have via 8, right? So this is how, and this is your terminal metal, right? Yeah, so this is the final structure of the MOS transistor in the lab, or if you do some measurement on the wafer level measurement. So you actually give your voltages at voltages to the terminal metal, right? And your transistor is way down it, right? So basically your signal is passed from the terminal metal all the way to the transistors. Okay, so any question here before we move to the next part?
Sir, gate connection is not shown. So, sir, is it connected in some other plane?
Which one?
Sir, gate connections.
Yeah, gate connection is not shown here. So that is inside the computer, right? So this is done in other means. If you take a cross section, basically, if you look at the transistor, uh, so means I could draw. If you draw the layout of a transistor, um, your source and drain contacts is one point and your gate contact is here. So cross section, in this case, the cross section is taken at this stage, right? So that you only see the source drain contact, right? You cannot see the gate contact, right? So, right? So if you take the
Yes, sir.
cross section here, you will see also the gate contact, right? If you take the cross section. So they are there. So if this direction is x, sorry, this direction is y you are talking about, and so basically then this is the z direction. So if you look at the z direction, so in the width direction, so your source and contacts and the gate contact, they are not in the same z, right? So they're in the different z's. That's the reason in cross section you cannot see.
Yes, sir.
All right. So this is about just to talk you about your MOS transistor. So so this course here. Um, so basically, uh, so you visualize the transistor in this way. So you when you visualize, so you have source and drain part, right? And you have your P substrate, right? So this is if this is NMOS, then I have P substrate. For NMOS, I have also a P well, right? Right, and then you have your gate, right? Then you have your spacer, right? Um, so so if I have a spacer, then I could let's do it properly, right? So then you have your extension and your source drain, right? Your extension and your source drain. So this is right, this is your gate. Then so this, okay, here I have silicide. So basically your this portion is silicided, right? And your gate is also fully silicided. And then you take a contact, right? So your contact is taken like this, right? So your contact is uh, taken like this, right? And your gate contact is taken like this, right? And this is your metal. Let's say this is your metal one, and this is a metal one. This is the gate contact, and this is your source, and this is drain. And also here also substrate contact is not shown. Um, so let me write down. This is n plus, right? So you have your isolation here. In this case, your isolation here. Then you take your contact to the substrate. So again, you have your P plus here. So this region is your substrate, right? So their substrate contact is also at the top, right? Right, and which is called body B, right? So this is the uh, typical typical transistor, right? So you just visualize this in head, right? Okay, when I talk about transistor, I have the structure, right? So all the contacts, source, gate, drain, and body, that are taken at the top, right? So even I cannot, when I draw the schematic, I give body contact here, but because I cannot give body contact inside substrate, right? So everything has to be at the top. So in typical, in the transistor, all the, I mean, you have to take in this contact, right? And this is done through, again, body is contacted through P plus, then your body contact, right? So when I talk about four terminal device, your transistor is this, right? Okay. So similarly for NMOS transistor, your source drain will be replaced by P plus and PUL will be replaced by NOL, right? Other things will remain same. All right. Okay. So before I go to the next thing, so now because we have discussed your transistor operation, we talked about threshold voltage, we talked about a lot of other equations. So now we'll go to short channel effects, right? So short channel effects. So before we go to the short channel effects, I'll just tell you about why we're worried about short channels, right? So why we are worried about uh, because you will hear about short channel effects a lot, because short channel effects degrade the device characteristic and blah blah, right? So let's talk about why you have to worry about short channel effects. So short channel effects is coming because of scaling, right? What is scaling, right? I'll just briefly tell you in this class, and the next class we'll talk about short channel effects, and we'll also talk about subthreshold characteristics, right? So before I go to go to scaling, right? Uh, so this I have taken from my older slide. So here, just to discuss about transistor fundamentals, right? I mean, let's recap the things, right? How does the transistor work? So basically, when I talk about transistor, so I have two regions, right? So we have two source and regions, right? For NMOS transistor, I have two regions which is full of electrons, and for a PMOS transistor, I have two regions which are full of holes, right? So when gate voltage is zero or gate voltage is a flat band voltage, the electrons are confined to the source drain regions, so they cannot flow to the substrate because of the energy barrier QVBI, right? So because of this energy barrier QVBI, they could not flow to the, because I have electrons. So let's say your gate voltage is your flat band voltage, right? And even if I give some voltage difference between source and drain, so there will be no electron flowing, right? Because because your electrons cannot go from source to the substrate or source to the substrate. So electron cannot go from N plus to P region because there is a barrier, right? So this energy barrier, we know this energy barrier is because of the PN junction, and the height of this barrier depends on the doping of P and N side, right? And this height of this barrier is always is high because one is your source and drain regions is N plus, right? When you apply gate voltage, right? So there is an electric field from gate to substrate, and this electric field uh, repels source and creates depletion region, right? So this electric field repels holes, and it also uncovers this acceptor ions. That means we have created depletion region, right? And see this. So the moment we have depletion region, so I have a potential drop in the silicon, and that potential drop I called Vx, right? And from the circuit model point of view, so you could see that we have the capacitance divide. So I have my gate voltage here Vg. So then I have oxide capacitance, I have depletion capacitance, and this is my Vx. And Vx in our case we discussed in the class. This is our surface potential, right? Right. So surface potential is nothing but the potential drop in the silicon, right? and there will be potential drop in the silicon if we have some electric field. No electric field, no potential drop in the silicon, no potential drop in the oxide. So this surface potential increases with increase in gate voltage because your gate is coupled to the surface through these capacitances, if you think from the circuit point of view. And we have also discussed in the last class, your psi s is nothing but Vg by 1 plus Cox by Cd, right? And this is Vg by this is Vg by M, right? So as you increase your gate voltage, your surface potential increases, right? Your potential drop in the silicon increases, your surface potential increases. So with increasing surface potential, your junctions are both the PN junctions are forward biased, and and there is a reduction in the energy barrier since these junctions are forward biased, and the electrons start coming coming to the substrate, right? So now this, since there is an electric field, these electrons are attracted to the surface and they accumulate at the surface. We call that region in the channel, right? This is a channel of electrons formed, right? Right? Actually, we create a channel, right? And that channel is nothing but a sheet of electrons sitting between source and drain. Now, if I apply your gate voltage, sorry, if you apply a potential difference, if you apply a potential difference, then this electrons will flow, right? So you could think of uh, you could think of this um, as a let's say I have two reservoirs, right? So you could think of it as two reservoirs, right? I could do it properly, right? So these are two reservoirs, right? Right. So basically, I have a channel, right? So right, but now for the um, let's say this is water. For the waters to flow from source to drain, I have to create a height difference, right? So I have to create a height difference. That means I have to pull it down. So if I have to create this slope, right, then the water will flow from source to drain, and that is done in this case by applying a drain voltage, right? When you apply a potential difference, there will be a gradient, right? There is a voltage gradient. The voltage gradient means there is a energy gradient. Energy gradient means your electrons will go from source side to the drain side. There is a current flow, right? And we also discussed this thing, right? Your current is charge into velocity, and we have calculated and blah, blah, right? So the main thing is your current is because of both gate voltage and drain voltage, right? If one of them is zero, then there will be no current, right? So your charge is proportional to gate voltage. Please keep it in mind. Your charge is proportional to gate voltage, your velocity is proportional to drain voltage, right? So, and your current is both charge into velocity, right? So without VGS or without VDS, will not have any current flow, right? All right. So when I talk about characteristics, right? Um, so we have three characteristics, so right? So we have transfer character. Okay, so three characteristic. One is your input characteristic, right? And your transfer characteristic and your output characteristic, right? Right. So a transfer characteristic, input characteristic is in the input port itself. So this is if you plot gate current as a function of gate voltage, right? So your input port is gate to source port, right? So if this is your transistor and this is your source and drain and this is gate, so your input port is between gate and source. Your output port is between drain and source, right? Sorry, drain because here the source is common, right? Um, so, so your input characteristic, right? If source is common, that means your input characteristic is between Ig as a function of Vg, right? Gate current as a function of gate voltage. Your transfer characteristic is your output as a function of input. So this is drain current as a function of Vgs because your source is common. So it will be Id as a function of Vgs. Your output characteristic is your output current and output voltage, ID versus VDS, right? So we talked about ID VDS and ID VGS earlier also. So if I do um, if you plot ID as a function of gate to source voltage, then you means you will have this curve, right? So this is at a particular VDS, at a particular VDS. So your gate current will increase after threshold voltage, right? So this is threshold voltage, right? And we know that ID is mu Cox W by L, VGS minus VTH into VDS minus half VDS square. This is our universal equation. But in the saturation, your VDS will be VGS minus VTH, and this equation will become mu Cox W by 2L VGS minus VTH square. Right? Okay. So, but here, if you look at this part, right, this is, so this part we called when the transistor is on, that means your VGS is more than threshold voltage, right? Right. But in this part, your VGS is less than threshold voltage. VGS is less than threshold voltage, and this part is your VGS is more than threshold voltage, right? So VGS, when VGS is less than threshold voltage, here the current is not actually zero, right? There is a current, but that current means we'll discuss this. This is called the sub-threshold region, right? Below threshold, right? So that means when VGS is less than VTH, we called it sub-threshold region, right? Right? And in the sub-threshold region, the current is not zero because see, when I'm applying VGS, right, a positive VGS, right? So even let's say VTH is zero point 0.4 volt, right? Threshold voltage is zero point 0.4 volt. At this point, let's say I'm applying a gate to source voltage of zero point 0.2 volt, right? When I'm applying gate to source voltage of zero point 0.2 volt, even the zero point 0.2 volt is less than 0.4 volt, the surface is not inverted. That means I do not have lot of electrons, but I have electrons, right? I will have electrons the moment your VGS is more than zero, right? Or more than flat band voltage, right? And these electrons will also flow because I have a VDS, the electrons also go. That means the electrons in this region, that means the current is not zero, right? There is a finite current, and that current we call the sub-threshold current, right? And that current is behaves like a bipolar transistor. We'll come to that point in the next class. So, if you look at your IV characteristic of a typical transistor, right? So, when you plot in the log plot, this is what how you should plot your transistor characteristic ID as a function of VGS, but this axis is log axis, right? And if this is your threshold voltage, right? So you will see your curve will look like this, right? ID VGS, right? In the log plot, right? So below threshold voltage, your current falls exponentially. Why it falls exponentially, we'll discuss in the next class, right? And this point, right? So when VGS equal to 0, right? This current we call the off current of the transistor, right? Right? So at gate voltage of 0 volt, whatever current we have, that current is the off current, right? And I know that off current we defined in the last class. Off current is nothing but your drain current when your VGS equal to VDD and your VDS equal to 0. Sorry. Your VDS equal to VDD and your VGS equal to 0 volt, right? That is your off current, right? And similarly, on the on current also you define, and this is the drain current when your VGS equal to VDD and your VDS is also VDD, right? Right, and we want, so on current is somewhere here, right? So your on current is somewhere here, and this is your off current, and we mostly concerned about this ratio, right? And this ratio is nothing but I on by I off, right? Which is a major factor in digital design, right? So when you're choosing a transistor, you have to choose a transistor which has a very high on current to off current ratio, right? All right. So so when you're means in design, right? So when we're talking about on current, off current, right? So these questions always come into mind, right? What is important? Your on current is important because on current. So let's say when I talk about a simple inverter, right? If I talk about a simple inverter, right? Uh, Means most of you have done VLSI design, you know, right? So inverter. So basically, uh, so when let's say this is VDD, right? When I give VDD here, right? That means my NMOS transistor is on, right? Okay, let's do in the other way. When I give 0 volt here, right? When you give 0 volt here, right? When you give 0, right? That means your PMOS transistor is on, right? When you give 0 volt, and this capacitor is charged, right? And this capacitor is charged, right? Right? And the capacitor is charged to VDD, right? So how fast this capacitor is charged depend on the on current of your PMOS transistor, because you see when I give 0 volt, this is for the PMOS, this is your source, this is your drain and your gate, right? So your VSG is VDD, and your and in the beginning in the so your VSD will also be VDD with time, right? So sorry, in the beginning when you give 0 volt, your VSD because was also VDD, right? So right. So how fast? So if you give 0 here at the input, the output will be 1, right? But how quickly when you give 0, how quickly the output becomes 1? That is your delay, right? And for that delay means basically delay is nothing but how fast this capacitor is charged, right? And how fast this capacitor charge depends on the on current, right? So in that sense, if you want high speed circuits, right, when you're talking about high speed circuits, very less delay, or let's say your microprocessor is operating at 3 gigahertz or 4 gigahertz or 5 gigahertz, that means how fast your output node is charging or discharging, right? So in that prospect, your on current is very important, right? And do you want your on current to be very high, right? But let's say when your device is not working, let's say your transistor is off, let's say your inverter is off, right? So your um, you have something like this, right? So let's say you have gone from or you give 0 volt and stay there, right? Stay at 0 volt, right? So when you give 0 volt and stay at 0 volt, right, that means your output becomes VDD, right? And if you look at this NMOS transistor in this case, right, you look at the NMOS transistor, the NMOS transistor, your VGS of NMOS transistor is 0 volt, but your VDS is VDD, right? Right. So so that means at this condition your current, as I told, right, so your there is a current flowing, right, and that current is the off current of the NMOS transistor, right? And if your off current is high, if your off current is high, that means this capacitor will slowly discharge, right? Even if so a capacitor will discharge, right? So in that case, your off current is important, right? And off current is also important because if nothing is happening, right, you're not. I mean, so you do not have any signal, right? All the transistors are off, right? Off means your power supply is on, right? So every transistor is drawing some current. That current is your off current, right? So in that case, your off current is important because off current is important in the standby mode, right? So if I give an example here, if I give an example. So let's say when I talk your mobile phone, right? So your mobile phone, let's say you are using a processor which has 2 billion transistor in that processor, right? 2 billion transistor, and your off current is very low, zero point 0.1 nanoamperes. Let's say means zero point 0.1 nanoampere is very small, 10 to the minus 10 ampere current, right? 10 to the minus 10 ampere current, right? But I have 2 billion transistor, even if I'm not doing any logic operation, right? The all the transistors are idle. In the idle condition, they are drawing I of current, right? So total, if I multiply 2 billion into 10 to the minus 10, right, it becomes zero point 0.2 amperes, right? 200 milliamperes, right? See, keep in mind, I am not doing anything, but still, whole IC, if I have 2 billion transistor, whole IC is drawing zero point 0.2 ampere. That means 200 milliamperes of current, right? Right? That is the power. This is the power of I off, right? Even a single transistor off current is very low. I'm talking about 10 to the minus 10 amperes, right? Zero point 0.1 nanoamperes, right? Still total idle current is 200 milliampere. And if your VDD is 2 volt, the idle power is almost zero point 0.4 watt, right? So you are not doing anything. Let's say your mobile phone, you are not doing anything. This is you have just kept it in a table, not doing anything, but it is drawing zero point 0.4 watt of power. If your battery capacity is 3000 milliamperes hour, so you could calculate how much time your battery will last, even if you are not doing anything, right? So, so this is, that means your battery, so if your capacity of your battery is 3000 milliamperes hour and your idle current is 200 milliamperes, so it will hardly sustain 3215 hours, right? If you're not doing anything in your mobile, right? Not doing anything, it's just kept in your table, right? So in 15 hours, your battery will discharge, right? That's the reason, even if you, I mean, or if you're doing some work with your mobile, it will discharge faster, right? So this is very important, right? Because when I'm talking about handheld devices, mobile devices, I don't want to charge those handheld or mobile devices very often, right? So from that point of view, your off current is very important, right? So there are two things. One is speed, one is your power leakage, right? So that's the reason speed and leakage are very important. So both are important. Ion is important, I off is important, right? But when we're talking about mobile device, right? So I off is more important because you don't want to charge it more often, right? But when we're talking about servers or high speed circuits, there you don't work them because those circuits are always connected to power, right? So there we worry about speed, right? I want to do my processing faster. I am worried about instructions per second, right? How many instructions I could give and the processor could do, right? That is your speed, right? On current, right? And off current is if you're not doing anything, how much power it is consuming, right? So that is your off. So for different application, both of these things are important, right? So that's the reason when I characterize a MOS transistor, right? When I characterize a MOS transistor, this uh, this is, I mean, both ion and IF are important, and we actually do it. I mean, we call that's the reason we plot on current and off current. That curve is called universal curve of a MOS transistor, right? So this is what when let's say the TSMC or some fab come up with a new technology node. So what they show us the universal curve. Okay, this is the universal curve of my technology, right? That means this is if I have a transistor which have this much on current and it will give this much off current, right? Right? But you could ask me questions, right? Universal curve, I told you, right? On current and off current of a transistor is fixed. That means I will only have a single point. For a single transistor, I will have a single point, right? Then how can I get this universal curve of a technology? So what is generally done is you have a nominal, you have your nominal transistor. Nominal transistor, let's say 180 nanometer technology, your nominal transistor is 180 nanometer long transistors, right? Right? That is your nominal gate length, right? But you also do subnominal transistor and supernominal transistor. So let's say you do supernominal transistor, right? So you go to 200 nanometer, 300 nanometer transistor, let's say, and you also go to subnominal transistor. You go to 150 nanometer, 100 nanometer transistor in the same node, right? Right? Then you measure the on and off current of all those transistors, your nominal transistor, your subnominal transistor, your supernominal transistors, right? So your on current here and off current here. So this is a log axis, this is the log axis, and this is the linear axis, right? Then you have 4 and 5 transistors. Then you plot these transistors, right? So you'll get a straight line, right? So that is your universal curve of the transistor. That characterizes how good your transistor is, right? So if you look at this curve, right, which one is better? I want high ion. So basically, if I want to use a transistor, I want to have very high on current but very low off current, right? I want very high on current but very low off current, right? Right. So my slope should be my slope should be as small as possible, right? So this is the slope of the universal curve, right? When I talking about a transistor has a very good universal curve, that means the slope is very less. That means if we have two technologies, let's say this is the TSMC's technology and this is Intel's, right? Intel's technology, right? So and both are 180 nanometer node, let's say 180 nanometer, 180 nanometer, right? But when you plot their universal curves together, let's say TSMC has this characteristic and Intel has this characteristic, right? But here you could clearly see TSMC is a very good, TSMC transistors are much better because at the same ion, right? So so at the same I of, let's say at the same I of, I have much better on current, right? And at the same on current, I have much better off current, right? So that's the reason this is how your technologies are compared, right? So let's say you want to compare TSMC technology with Intel's technology, you just plot the universal curve, right? So you have your PDK with you, and you just measure the ion, you just simulate the on current and off current, and plot it, right? Then you could compare different technologies, right? And this is so this is how the different foundries compare their technology with their rivals, right? Let's say if TSMC wants to compare his technology with Intel's technology, they just plot universal curve and they advertise, okay, see, I have a better universal curve, please use our technology because Intel's technology is not good, right? So this universal curve, I mean, you will not find any description about universal curve in the books, right? This is, I mean, because they are very industry specific curves, right? So book does not show you the universal curve. But if you see the research papers has lot of, they plot always universal curve, right? Okay, so basically we know about universal curve. A universal curve of a technology is nothing but when you plot I on and I off, right? And but let's go to scaling, right? So because means we, as human being, we always want to progress, right? So right, if you have a better, if I have a particular transistor at this point of time, I want to have a better transistor in 2 3 years down the line, right? So that's the reason we want very hard to make our technologies better. So to give an example, if I look at the first microprocessor, right? When you talk about first microprocessor, which was done in 1971, so I have a 4-bit microprocessor which has a clock frequency of 740 kilohertz. Number of transistors is 2,300, and gate length was 10 micrometer. And if you look at the number of transistors per millimeter square of area, I have around 190 transistors per millimeter square. This is the first microprocessor, right, in 1971. But if I look at now, right, so here also I have compared to last 22 years. So I have taken Intel Pentium 3 and Intel Core i7, 9 Core i7. So so this is so Intel Pentium 3 came in 1996, and this is 2018, right? This is the 22 years because I have used that time this slide because 1996 where I have used my first computer, right? And my first computer has an Intel Pentium 2 processor, right? I was in BTech second year that time, and I was exposed to the computer, okay? And we know, means we heard that, okay, this has an Intel Pentium 2. No idea what was Intel Pentium 2 that time, right? We just used it, right? And then Intel Core i7, which came in 2018, right? If you compare this last 22 years, right, in 96 and 2018, and in 2020 we have better processors now also, right? So Intel Pentium 2 has 50,000 instructions per second, right? But if you look at Intel Core i7, this is 300 billion instructions per second, right? Very fast processor, right? Intel Pentium 2 was a single core processor. This is an 8-core processor. If you look at the number of transistors was 7.5 million in Intel Pentium 2, but number of transistors in Intel Core i7 is 4 billion, right? But you look at the die area, the area of your circuit, area of the chip, right? Area of the chip is still the same, right? Even lesser, right? Intel Pentium 2 was 195 millimeter square, but Intel Core i7 is only 180 millimeter square IC, right? Right. So if you look from the dimension point of view, you have your dimension is less, right? But you have more number of transistors, right? And if you look at the transistors per millimeter square, which is a metric everybody uses, right? So you have 35,000 transistors per millimeter square of area. Now in Intel Core i7, it was 23 million transistor, right? 23 million transistors per millimeter square. And but if you look at the technology node, it was 350 nanometer CMOS technology in 96, and we are using 14 nanometer CMOS technology, right? 14 nanometer in that minimum transistor 96. Right? So this is how the things have evolved between 96 and 2018. When we are talking about 2020, 20 or 21 now, so we have ICs which have 8 billion transistors, right? Now we have microprocessor ICs having 8 billion transistors, right? And we are using 7 nanometer CMOS node, right? 7 nanometer, 5 nanometer CMOS node, right? So this is how the things have improved. And how is this possible? This is possible because of scaling, right? So we're talking about in a millimeter square of area, I have 35,000 transistors. Now I have 23 million transistors, right? That means the area of the transistor has reduced, right? And that reduction in area, we call it scaling, right? That means we are scaling, we are reducing the size of the transistor. And what do you mean by scaling, right? So here I have taken two layouts, right? If you look at the left hand side, I have a transistor, and we have actually I have two transistors, right? Two transistors. This has two transistors, right? Because two transistors is generally used just to look at the pitch, right? So so here this transistor has a length of L, right? Length of L, right, and width of W. And the transistor, if you look at this has two transistors, right? And if you look at the transistor area, so the area will be between the area, when you calculate area, right? Area is between these 2 points, right? Then you measure, right? So and right, and so basically I'll just tell you. So the area of a transistor is nothing but contacted poly pitch. This is the poly pitch into metal pitch, right? So if you multiply poly pitch, your gate pitch, right? Your gate pitch and metal pitch. Why gate pitch into metal pitch? So pitch is the distance between two consecutive gates, right? So this is your contacted poly pitch, the distance between two consecutive gates, right? So your gate is drawn like this, right? So you see, your gate is drawn like this, right? Your gate is drawn like this, right? Right. And your metal one, I told you, right? Metal one is drawn like this, right? So this is your gate pitch. This is your poly pitch, contacted poly pitch, right? And this is your metal pitch, right? Your area of the transistor is basically poly pitch into metal pitch, right? Because this might be the area of one transistor, right? Right? Poly pitch into metal pitch. So when you talk scaling, right? When you scale the transistor, that means we reduce the poly pitch, the pitch between two gate polys, and also we reduce the metal pitch. That means we reduce the dimension in x direction as well as z direction, right? So this is our y direction, and this is your z direction. So we reduce the dimension in both directions. That means we just shrink the dimension in y and z direction by a factor of k, right? So if your width is w, the scaled width becomes w by k, right? If your length is l, your new length will become l by k, right? And this k is the scaling factor, right? And if this 1 by k is 0.7, right? So you see, your poly pitch is reduced by a factor of k. Your metal pitch also reduced by a factor of k, right? And this is my area, and new area becomes old area by k square, right? And if this k square, if k is 0.7, right? And I have 0.7 and 0.7, that means 0.5. The new area, right? Sorry, if 1 by k is 0.7, right? So if 1 by k is 0.7, right? So your new area will be old area into 0.5, right? Right. So this is the scaling, right? This from there. So that means a new generation, when I'm talking about 180 nanometer and new generation is 130 nanometer, right? So the area has reduced by zero point 0.5. That means if I design an integrated circuit, same integrated circuit using 180 nanometer technology, if I have an area of 100 millimeter square, if I use 130 nanometer CMOS technology, my area will be 50 millimeter square, right? This is the scaling, right? Scaling is nothing but reducing all the dimension by zero point 0.7, right? When I reduce all the dimensions by zero point 0.7, your area automatically reduced by, I mean, 0.5. That means uh, you in the same area, you could have twice the number of transistors, right? So this is the scaling. And I mean, if you look how this technology nodes have evolved between 1971 and 2022. So we started with 10 micrometer technology, right? So we started with 10 micrometer technology in 1971, and now we are talking about 5 nanometer technology, right? 5 nanometer CMOS node, which is 2022. It has not come yet, but it will come in next year, early next year, or mid next year, right? But in between, we have gone to different CMOS nodes, right? So we have 7 nanometer CMOS node, 10 nanometer node, 40 nanometer node, 22 nanometer node, 32 nanometer node, 45, 65, 90, 130, 180, 250, 350, 600, 800, 1 micrometer, right? These are different CMOS nodes. This is how the things have been scaled over the years, right? So when I was doing my BTech, right, in this range, right, 95 to 99, right, in this time frame, so they are we are 250 nanometer CMOS node and 180 nanometer CMOS node, right? Right? And when you people are now seeing only 40 nanometer, 10 nanometer, 7 nanometer CMOS node, means we still use other nodes, right? 180, 130 is also used nowadays for different applications. But what is the difference, right? So somebody yesterday Om was asking me, ki kya difference means, like I don't remember who you were asking. I think this is Om. So what is the difference between 90 nanometer and what is the difference between 65, right? I mean, what is there in the name, right? So in 90 nanometer kya hai? What does 90 nanometer CMOS not define? I mean, it tells you, right? So it is nothing, right? So basically, because see, somebody came with a name, right? So let's say when I'm talking about 800 nanometer, right? Right. So if 800 nanometer is the node now, right? Um, the next node, right? Let's say company has 800 nanometer node now, and they want to go to the next CMOS node. And the next CMOS node, since this zero point 0.7 is proposed, this is famous. We call it Moore's law, right? Moore proposed that okay, the number of transistors in the same area will double every new generation, right? So from there, this zero point 0.7 came into factor, right? In the same area, I can have twice the number of transistors, right? So this is this famous Moore's law, right? Right. So this zero point 0.7 stuck in our mind, right? So industry, the semiconductor industry, so this zero point 0.7 is there, right? And zero point 0.7 is a very unique number for semiconductor industry, right? So if this is 800 nanometer now, so the next node will be 800 into zero point 0.7, right? And 800 into zero point 0.7 is how much? This will be 560 nanometer node, right? Okay, so people, okay, this will not be 560 nanometer node. So basically, you could name it as 600 nanometer node, right? So this naming is nothing but zero point 0.7 scaling, right? So you could see, right? 350, let's say 350 into zero point 0.7, right? What is 350 into zero point 0.7? Right? 350 into zero point 0.7 right? So this will be 7 into 5, 35, 7, 24, right? So 24, 245, right? 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 350 into 0.7 is 245, right? And this is 250 nanometer node, right? Similarly, 250 into zero point 0.7 or 250 into zero point 0.7, this is 175, right? And that's why this is 180 nanometer CMOS node. So there is nothing in this 180 nanometer name, right? It didn't come from somewhere, right? So this is just the zero point 0.7 scaling, right? And similarly, 180 into zero point 0.7, right, is 126, right? This is how this 130 nanometer name came from, right? 130 nanometer is nothing but 180 into zero point 0.7, right? And 130 into zero point 0.7 is 91, right? This is where the 90 nanometer came into picture, right? Right. So this is just the name just came from the scaling. There is nothing else, right? So 90 nanometer doesn't mean anything, right? The name was 90 nanometer because earlier node was 130 nanometer, right? And the next node was 65 because 19 to zero point 0.7 is 63, right? And this name is 65 because earlier node was 90, right? It was just a convention. There is a lot of debate happening now because as one of you asked, right, what do you mean by 90 nanometer? I told you 90 nanometer doesn't mean anything. This is just a name, right? So there are a lot of debate going in the industry. There is a misconception that when I'm talking about 7 nanometer, that means my minimum dimension, minimum gate length is 7 nanometer. That is not true, right? That is not true, right? So this is just a name, right? Right. So since the earlier node was 10 nanometer, so 10 nanometer and zero point 0.7 becomes 7 nanometer. 7 nanometer zero point 0.7 becomes 5 nanometer. 5 nanometer is zero point 0.7 becomes 3 nanometer. Next node will be 3 nanometer, right? And the next 3 nanometer बाद 2 nanometer आएगा because 3 into 0.7 is 2 nanometer. 2 nanometer के बाद 1.5 nanometer आएगा, उसके बाद 1 nanometer node आएगा, right? Right? So this is just a name, right? Nothing else, right? So you could see it here. So see all these things is just 0.7x, right? So the name comes from this 0.7x scaling, right? And when you do the 0.7x scaling, so your area will reduce by half. And this is the famous Moore's law because every new generation will have twice the number of transistors in the same area, or uh, or the transistor area will reduce by half, right? Right. So this is how the transfer dimensions over the years. And this is the last slide I'll show today because we have already 12 minutes past 12. So here you see, as I was telling you, uh, so this white line is your physical gate length in different technology nodes, right? And this red line is your nodes, right? Node name, right? And this is following by a zero point 0.7 scaling, red line. But the physical gate length, actually gate length that we use, right? If you talk about 130 nanometer node, so the minimum gate length is 70 nanometer. So if you tell, okay, this is 130 nanometer technology, minimum gate length is 130 nanometer, this is not correct, right? Minimum dimension is 70 nanometer, right? So let's go to 10 nanometer. 10 nanometer, the minimum dimension we're talking about 14 nanometer, right? Your gate length in 10 nanometer technology is 14 to 15 nanometer, right? We cannot scale it, right? So your gate length has almost stagnated. I mean, basically this has saturated, right? You cannot really scale your gate length further, right? Even when you're talking about 5 nanometer CMOS technology, in the 5 nanometer CMOS technology, your gate length, minimum gate length that we're talking about is 12 nanometer, right? Right? Minimum gate length in a 5 nanometer CMOS technology is 12 nanometer, right? And even 3 nanometer CMOS technology, when I talk about nanosheet FETs, all those FETs, we are still using 12 nanometer, 10 nanometer gate length, right? So these names doesn't have any meaning. This is just a name, right? Just when somebody tells you 180 nanometer CMOS node, this is just a name, right? There is nothing else. 180 nanometer, that name will not give you much information. If you really want to know the information, right, about the technology, go and read the design manual, right? So every foundry gives you the design manual, right? So you could download from their website. If you want to use 180 nanometer CMOS technology, you could download the PDK from their website, and PDK will give you every information. PDK will tell you what is the minimum dimensions you could use or not, right? By just looking at the name, you could not know anything. And the last thing I'll tell you, when you're talking about PDK, right? Let's say 180 nanometer PDK. This is where all the rules have been defined, right? What is the minimum dimensions? What is the space between different layers and all those things. So 180 nanometer of TSMC, let's say, and 180 nanometer node, 180 nanometer PDK of, let's say, Intel, right? Right. So the name is same. If you look at the name is same, right? But the PDKs, if you look inside PDK, the dimension might be different, right? So PDKs, the name is same, but the PDKs are foundry specific. PDKs are company specific. PDKs are your fab specific, right? So and that tells you the capability of the fab, right? How low they could go in this same technology, right? Right. So that's the reason I told you कि name में कुछ रखा नहीं. This is just a name. 180 nanometer is just a name. If you want to know more about the technology, what are available, what is not available, then go and read the PDK. The process PDK is nothing but a process design kit, right? This is the process design kit, and this PDK will give you all the information about that technology, right? Right? And PDK of two different companies, even the name is same, might be different, right? Even if 180 nanometer CMOS node, your transistor may behave, TSMC transistor may behave differently compared to Intel transistors, right? Right? Their universal curves might be different, right? But they just tell you, okay, this is 180 nanometer CMOS node, but it is, but if you go inside, they are foundry specific, they are company specific, right? Okay, so I will stop here today. Right. So any questions? We could have a discussion.